For this lesson, we're going to be looking at rate in the fluid system. Okay, so this will be working with liquids. More specifically, it'd be fluids, which would be like water or something like that, and then gases. Because remember, a gas is still a fluid. A fluid is anything that takes the shape of the container it's in. Okay, so we're going to be looking at volume flow rate, mass flow rate, and then what those equations are that go along with this, and I'm going to be using V rather than Q. Okay, and then we're going to be using them to find values and measure rates in a fluid system. Okay, so here is our bell ringer to think about. So what is flow rate, and why is it important for a technician or somebody that works with something like that to understand flow rate when working with a flood control dam? Okay, so we have a specific example here. A flood control dam is what we're looking at. So flow rate is going to be the volume of the liquid moved over the time it takes to move that volume. Okay, if we're looking at maybe a river or something like that, it's going to be the cross-sectional area of the channel. So say we have a channel going, we're going to have to find the area going across and the average depth of that. So it's going to be the cross-sectional area times the speed of the water. Okay, so that's flow rate. Those are two different ways we can measure it. We can also measure it in mass over time when we're working with gases. But we want to think about why it's important for a technician to understand flow rate when working with a flood control dam. Well, they need to understand how much force the dam can take and how much liquid they can push through the dam at one time. So if they have a stream or a river upstream from the dam, okay, so here's our dam with our floodgates, and this water starts to move too fast compared to the water coming out of the floodgates, then they're going to have problems. So they have to be able to measure the flow rate of this water in order to understand if the dam is going to hold that water or not. Okay. So let's look at what flow rate is again here. So why did the rate of a fluid matter to you today? So think about something that you may have done or used today that made flow rate important to you. So first thing that comes to my mind is a faucet. We have liquid moving in our house. Another time might be a shower. So the flow rate of the fluid determined how much water came out of the shower head at one time. You don't want to be getting blasted by water in your shower. Okay, so if you got a drink from maybe a water fountain or something like that, you don't want to get blasted in the face by the water fountain, right? So we have to have the pipes at a proper size, and we have to have the pressure in the pipes at a proper pressure, so that way we don't get blasted in the face. Okay, and that comes from determining flow rates at the point of where the water goes into the system and where the water comes out of the system. Okay, so those are two really important things that you may have used today. And a third one is washing your hands. So I think it's really irritating sometimes when you turn on the faucet and you just get blasted by the water that's coming out there, and it gets all over your pants and all over your shirt. So that's another scenario where it's important to understand flow rates. So you unintentionally know flow rates by changing the little levers on the faucet. So if you have your faucet and then you change the lever, so hot and cold, right? You're not going to open this thing up 100% because you might get too much water coming out of there. So you're unintentionally controlling the flow rates when you move this valve, right? So what are the two things that determine flow rate? Let's look at a shower here specifically. Okay, so you can kind of think of them off the top of your head. I have them listed here below, but it's the pressure of the water and type of shower head. So we have these things called low flow shower heads. It's going to have smaller holes, which is going to increase the speed of the water, but it'll decrease the flow rate. Okay, because you guys know that we get charged per maybe liter or gallon or whatever it is at the water treatment plant. They charge you so much per gallon used. Okay, so if we have less volume moving through our shower head, then we'll be charged less because we won't be using as much. Okay, so it's going to cost less for the shower. So that's why it's called a low flow or a cost efficient shower. So looking at another example here with, we have a big drum that has a small pipe and a larger pipe on it. So one pipe is 6 inches, the other pipe is 1 inch. So what's the difference? What's going to change here? So flow rate depends on the size of the pipe. Okay, so you can think of there's a lot more water coming through this one than there is that one. right? So how much fluid passes through a cross-sectional area of the pipe? So I mentioned that when I talked about the river scenario. The cross-sectional area would just be finding a chunk of this pipe. So I'd measure the diameter of this pipe and I'd figure out the area of that chunk, and then I can take the area times the speed of the water that's coming out of that pipe, and that'll give me the flow rate of that pipe. So larger pipes, like our 6-inch pipe here, is going to have a higher flow rate. Smaller pipes are going to have a lower flow rate because they're smaller, they're not letting enough water go through them, or not letting as much water go through them. Now if you think of speeds here, the speed of this water is probably going to be a lot less compared to the speed of this water because smaller pipes also increase the pressure. So there are two things happening there. We have the flow rate and then we have the speed of the water coming out due to the pressure. So those are two different things to think about. So fluid speed is just the speed of the fluid and does not give information of how much is moving. We have to use the fluid speed, so that could be meters per second, how fast it's moving in meters per second or something like that. We have to use that speed in order to figure out flow rate. So for gases, all right, so we had liquids and now we have gases. Mass flow rate is a better indicator than volume flow rate, okay? And the reasoning why this is, well, temperature and pressure can influence the volume of a gas drastically. If you remember, we had our gas law, P1 V1 equals P2 V2. The pressure and volume can change, or the pressure can change the volume, right? Or the volume of the gas can change the pressure or the volume of the container. Temperature can also change things. So think about if you have a balloon and maybe that balloon is left in your car overnight and it got close to freezing. When you go out there and check on that balloon, it's going to be kind of deflated and sitting down on the ground. But then when you take it back in the house, after a while when it warms up, it's going to be back up floating again because the temperature can affect the volume and the pressure of that gas. Okay, so that would be mass flow. So mass flow or volume flow are acceptable for liquids. Okay, so you can use either one for liquids. All right, so mass flow and volume flow will work for both ones. Liquids do not have a drastic change in volume under normal temperatures, so you wouldn't use under crazy temperatures like heating water up to 6,000 degrees Celsius or something like that, or you wouldn't use it below freezing temperatures, okay, because that would change stuff, so you'd have a normal temperature to use when you're measuring things. So the thing to remember from this slide is that mass flow rate is what we're using for gases, and mass flow rate or volume flow rate will work for liquids, okay? So let's look at the equation. The volume flow rate is going to be change in volume per unit time. Volume flow rate equals change in volume, which is the delta V, over a time interval. So remember, this could be where you have a final volume minus an initial volume, so you have the amount of volume that's changed over a time interval. Usually this is going to be from 0 because it's going to say my elapsed time was a certain amount of seconds. So volume, remember, is going to be cubic things, so cubic meters, cubic centimeters, cubic feet, cubic inches, liters, or gallons. And the volume flow rate is going to be one of those volume measurements divided by a measurement of time. So cubic meters per second, cubic feet per minute, liters per hour, something like that. You might see every once in a while, maybe if you're a fisherman or something like that, where you have CFS, or if you go look at like some kind of a flood control dam, you'll see that. So that is cubic feet per second. So that's usually what they use to determine the strength or how much water can go through a dam. They're going to use CFS or something like that. So the amount of fluid that is moved is the displaced fluid. So if we did this right here, this portion, so if we did final minus initial, that would give me the fluid that is displaced. Okay, so that's just how much fluid is moving per that unit of time. Okay, so the next one we talked about was mass flow rate. So it's the mass of a fluid moved per unit time. So that's going to be the change in mass over time interval. And most of the time, you're just going to be given an amount that moved. But remember, we still could have final minus initial for mass, and we'd have that unit of time. And it could be slugs per second or kilograms per second. This is probably the one that we're going to be using more often. It would be kilograms per second. This is another English measurement, but we're going to be using kilograms per second for mass flow rate. And remember, this is going to be used for gases. So mass flow rate will be used for gases. some ways to measure fluid rates. You're just going to have possibly some containers. So maybe you have a gallon jug, and you're going to turn on your faucet and fill that gallon jug up, and you'll take the amount of time it takes to fill that gallon jug. So you would have your change in volume be 1 gallon over, I don't know, let's say it took us 30 seconds. So it'd be 1/30th gallons per second if we wanted to do it that way. If we want to find an average flow rate, that would be the volume or mass of the fluid collected divided by the time interval, which is just what we did here. Okay, so that could be average, and usually with a faucet, this is going to be going at the same rate most of the time, so it would give us the average flow rate. And another tool that we could use is a flow meter. Okay, so you can look these up. They actually use flow meters in hospitals to get for breathing treatments for patients, if that rings a bell in your head. It has a tube here with some kind of a measurement line or something like that, and then the patient is going to blow into there, probably more of the air down here. The patient will blow into this part of the tube, and it'll raise that measuring piece, and it'll tell you how many liters or something that the person can blow in a certain amount of time. And that's what we use for breathing treatments for patients. We want to get a higher lung capacity. So again, this would be what a flow meter would be. This is a more simplified version than the one that I drew, but the patient would blow into that. They would reset this little notch down to here, and the patient would blow into this nozzle here, and then that little red mark would go up to about where their peak flow would be, and then that would tell you how many units that the person could express from their lungs. Okay, so let's look at a couple examples here after we write these equations down, make sure we have these. So volume flow rate is change in volume over time. We covered that already. And mass flow rate is change in mass over time. Okay, remember this was delta V over time, and this was delta M over time. Okay, so another way we can calculate volume flow rate is going to be area times speed. So this is area times fluid speed. So cross-sectional area, remember if you had a pipe or something like that, you would take a chunk of that pipe, you'd figure out the area of that piece, and then how fast the liquid is moving. We'd multiply those two values, and that's what we would get for a volume flow rate. Okay, and another way we can use for mass flow rate would be fluid density. So remember that's that rho times the cross-sectional area of wherever the fluid is coming from times the fluid speed. Okay, so this is rho, this is area, and this is velocity or speed. Okay, and then there's some conversion factors to know. You'll be given these most of the time, but these would be some nice things to know if I go from gallons to inches, gallons to feet, and gallons to cubic meters. So, example number 1. A tank holds 10,000 gallons. It takes 4 hours or 240 minutes to fill the tank with water. What is the volume flow rate through the pipe in gallons per minute? Okay, so volume flow rate is going to be change in volume over time. That's our equation. So our change in volume is going to be that 10,000 gallons. We're moving 10,000 gallons. Okay, and it takes us 4 hours, which is equivalent to 240 minutes. So that's the time that we're going to be using. So 240 minutes. So it's as simple as just dividing those two values out. So when you do that, you get 41.67 gallons per minute. So that's the volume flow rate of the tank, or of the water going into the tank. Okay, so let's look at a mass flow rate example. So we have 180 kilograms of ammonia gas flowing through the cooling coils of a refrigerated truck in 6 minutes. So what's the mass flow rate of the gas? And just to keep our variables or our units, whatever we're using, to look nice, I'm just going to do mass flow. So this is my mass flow rate. That's going to be change in the mass over time. Okay, and again, remember, there isn't really a change in mass written here. It's just a certain mass that's moving. So we're going to be using that 180 kilograms, and then it's moving in 6 minutes. Okay, so we do 180 divided by 6, and then you're going to get 30 kilograms per minute. Okay, and we could convert this to seconds if we wanted to. We'll just leave it since it doesn't specify anything beyond that. So the mass flow rate is 30 kilograms per minute of this ammonia gas. Let's check out another example. So a drainage channel moves or measures 2 meters across and 0.5 meters average depth across the channel. Okay, so here is our channel. Let's kind of draw this out so we can kind of see what we're looking at. All right, so it measures 2 meters across, and then the average depth is 0.5 meters on the channel. During a moderate rain, the water in the channel moves 2 meters per second down the channel. So when we get a rain going, we got that water, and its speed is 2 meters per second. Okay, so if you remember the other equation for volume flow, so it's the cross-sectional area times the velocity of the water moving down the channel. So we have a cross-sectional area that we can figure out. So it's if I took this chunk right here and I calculated the area of this chunk and I multiplied it by that velocity there, that should give us the volume flow rate. So area is just going to be length times width here. Okay, so it'll be 2 meters times 0.5 meters. That's going to give me the cross-sectional area of that channel times the velocity, which is 2 meters per second. And if you look at the units here, this is why this works the way it does. We have meters times meters times meters. Okay, so our final answer is going to be cubic meters per second. So the seconds is the only thing on the bottom. So 2 times 0.5 is 1 times 2. That's going to give us 2 cubic meters per second. That is the volume flow rate of the channel. And again, this is the cross-sectional area of the channel. That's what we're going to have to figure out. So you're going to have to take a length times the width, or this would be maybe a width times a height, if you will, for that channel. So let's look at one more example. Alright, so an air conditioning unit takes 20 minutes to fill a room with cold air before the thermostat turns it off. The mass of the air pushed into the room is 1.3 kilograms per cubic meter. So we want that. And the dimensions of the room are 10 meters by 15 meters by 2.5 meters. What is the mass flow rate of the AC unit in kilograms per second? All right, so this one's a little bit more complicated. We're given dimensions of the room, we're given the mass of the air pushed into there, and then we're given a time. So we want mass flow rate. That is going to be, so mass flow is change in mass over time. We're going to have to figure out the mass of all the air going into the room. So in order for us to do that, we're going to have to figure out the volume, right? So we're kind of connecting the two equations together a little bit. We want the volume of the room. So big V sub room is going to be 10 meters times 15 meters times 2.5 meters. That's going to give me the volume of that room. So the volume of that room is 375 cubic meters. And now we're going to take this and multiply it by the mass of the air going into there, and that's going to tell us how many kilograms of air we pumped into that room. Okay, so we'll take this, that volume times that, this would be our weight density, right? So our weight density is 1.3 kilogram times cubic meter. And then when we multiply those out, we get 487.5. And that is going to be kilograms because our cubic meters canceled out. So this is the mass of the air that goes into our room. So now we can figure out our mass flow rate by using that mass and that time. Okay, so mass flow is the change in mass, which is 487.5 kilograms over the time, which is 20 minutes. So we'll just divide those two, and you're going to get 24.38. And then we have to think about our units here. We have kilograms and minutes, so that is kilograms per minute. Okay. So some other things to think about before we are done. The rate in the fluid system, we think about pipe diameter, flow rate, and fluid speed. How are they related? So large pipes or large diameter pipes, the speed is going to be slow, but the flow rate is high because it's going to be allowing more fluid. It'll have a greater volume of fluid passing through that in that unit time. The small diameter pipes will have a smaller volume, but the speed could be higher because more work is done and the pressure, it could be more pressure on those smaller pipes. Okay, so thinking about an application, this is why city water pipes are going to have large diameters. they're going to have to meet the high demand for water. So coming out of the water tower, you have a pretty massive pipe, but then it kind of reduces down when it goes to the people's houses. So another thing to think about is using fluids from a storage tank. Okay, so where should we place the tank if we want to get fluids out of a tank? The tank should be as close to possible as where you want the fluids to be, and you want the smallest length of hose if you want the most efficient setup. Okay, because the flow rate is going to be reduced when you have to travel or you have to push liquids through a longer distance. So that's comparable to electricity. So remember we talked about if you have a longer wire, then that could produce more heat because of the friction it takes to travel through a longer wire. Okay, so we want less friction. That'll make a more efficient system, and the motor won't have to work as hard if you have it right next to where you're dumping it. Okay, so those are some ideas for a rate and a fluid system. We covered a few problems, and we looked at a few systems. To finish out, I have a few areas where you might think about rate in a fluid system where it might be important. So these are things you might want to think about. So a bottling machine, city water supply, air compressor, water purification systems, a refrigerator, ice maker, and vacuums. These are all the vacuums are going to use, like the air pulling through it. Air compressor obviously is going to be using air, but we want to make sure that we can control the air going through these, because if we can't control the air going through an air compressor tool, it's not going to work, right? It's not going to have enough pressure to maybe put a nail in a piece of wood or something like that, or it's not going to have enough pressure to fill up a tire, right? So controlling the flow rate with vacuums, if you don't have an adequate flow rate pulling the air through the vacuum, it's not going to do anything, right? So in like an ice maker or something like that, you want a specific amount of water over a specific amount of time, so we really have to control that volume flow rate, so that way we don't overflow the ice maker and it just makes a big old mess. Okay, so that's the kind of idea we want to think about with these. But technicians and engineers need to figure that out when they create their machines, so they have to modify the size of pipes, pumps and motors and stuff like that. So hopefully this helps you understand rate in a fluid system a little bit better. Thanks.